OK, so let me remind you what we were talking about last time. So we were discussing the example of DIS in the bright frame. And the way we led into this example is we talked about renormalization group evolution of the heavy to light current. We saw that it had this cusp anomalous dimension, but it was a multiplicative renormalization group evolution. And I said that that happened because we only had one collinear gauge invariant object in our operator. And then I just wrote down an operator that looked like this, and I said, there's one that has two. If we run that object, we will get a renormalization group equation that involves convolutions. And I said that that's going to give you the renormalization group evolution of the parton distribution function. And we wanted to explore that. And so in order to explore that, we should think of some process that has the parton distribution function in it, so we can really make sure we know precisely what the operator is. And that process is DIS. That's the simplest process. So we started thinking about deep inelastic scattering in the bright frame, which is this frame where Q of the photon has that form, just a component in the z direction. And in that frame, the incoming quarks in the proton, quarks and gluons, are collinear. An intermediate state, the out state, the x state that's going out, is hard. So you can think of the, if you were to draw perturbative diagrams, you'd draw them like this. This propagator would be hard. It would have a hard momentum. And then you would have loop corrections that could also be hard. In the effective theory, you don't really have to think about what diagrams. You just write down the lowest possible dimension operator. And everything that's a loop that's hard goes into the x, which is the Wilson coefficient, if you like. And likewise, we also get not just external quarks, but external gluons from diagrams. In the full theory, it would involve a quark loop like that. OK, so this is going to lead to the quark PDF, and this is going to lead to the gluon PDF. And we decided we would do the quark one in some detail. So this is kind of writing out now the operator and the Wilson coefficient in kind of a combined notation, where this W plus is W plus and minus, or W1 plus and minus W2. And then we had one more formula. It's kind of where we ended. So we have a collinear proton, and then we have this operator. And then we have the collinear proton again. And this matrix element can be written as follows. So this is the last formula we had last time. So some things here are just conventions, but other things are important. Well, everything's important, but some things are more important than other things. So this quark here has a flavor. It could be an up quark, could be a down quark. Let me denote that by an index I. This proton here is collinear, and really all that matters for this example is that we have some large, we can think of it as a massless proton even, but as far as its momentum is concerned, we can think of it as massless. So really the only momentum that matters in here is the minus momentum. So minus, which is m bar dot p, and that's what this is, m bar dot p. Bar dot p is capital P. OK, so capital P was the proton momentum. And we can think of this state as just carrying a large p minus. All the other components don't matter for this matrix element. It's a forward matrix element. Both states carry the same large momentum. And that's what led to this delta function here that says the W1 and W2, with the sign conventions we have, this guy has the opposite sign convention. And so if it's forward, these two guys have to have equal and opposite momentum, so that the sum is 0. And if you take into account the sign, then that means W minus is 0. So that's what that delta function is doing. And then the sum is something that's not constrained by the matrix element. And so the sum could either be positive or negative. If it's positive, we can say that it's some fraction of the proton momentum, because this is a quark inside the proton, and it carries some momentum, but it can't be more than the proton. Otherwise, we would get 0. So it's some fraction, and that fraction is defined to be c in this formula. And the reason there's a 2 is because I'm adding the W1 and the W2, which are equal. OK, so this is the momentum fraction. And then we can have an arbitrary function of that momentum fraction. Nothing stops us from writing that down. And that's kind of where we got to. Now, you can, so on general grounds, you can argue that that's the most general thing that you can write down for this matrix element. And I tried to argue about why that's true. From charge conjugation, you can actually do something more. So you can let charge conjugation act on these operators. And you can prove, since charge conjugation is a good symmetry of QCD, you can prove that that relates actually the quark and antiquark operators in the following way. So quark and antiquark operators are switching signs of W+. So if I switch the sign of W+, that's going from quark to antiquark. And basically what happens in the operator when you do charge conjugation, remember that chi goes over here to chi transpose, and the W switches sign. So basically what charge conjugation is doing is taking W1 to minus W2 and W2 to minus W1. And that's why the W plus switches sign, but the W minus doesn't. And then there's an overall sign just because the field from the fields, sort of from the usual charge conjugation transformation of the fields for a vector current. OK, so there's a all orders relation between the Wilson coefficients. So really, when you do the matching, you really only need to do the matching for the quarks. So if you wanted to do a matching calculation, you do a matching calculation for the Wilson coefficient with positive W plus. You could do it for the antiquarks as well, but you would just be basically wasting time. Now, last time we went through the kinematics of the bright frame a little bit. And this n bar dot proton momentum is actually q over x. So we could also write this formula like that. And so you see that W plus is actually something that's c over x, York in x, which is an external leptonic variable. Now, there was another index over here, J, which we talked about last time. And that had to do with the fact that we're taking the forward scattering graphs, which are a tensor, and we decompose that into two scalars, multiplying things that had indices. There was two possible things that we could write down. And the index J is just this 1 or 2. And there was a similar decomposition in the effective theory. We could think of decomposing the effective theory as a scalar in terms of the scalar operators, which are these guys, with some coefficients that have some indices then multiplied by some tensor. So these guys don't have indices, but I could just multiply them by effectively the kind of effective theory versions of these tensors, and so that's why there's a J here. Is that clear to everybody? OK, so there's various indices, I flavor, J for tensor decomposition, and then a bunch of momentum indices. So when you go through the analysis of trying to find a formula for, say, T1, it's going to be related to C1. And T2 will be related to C2. OK, because this guy's a scalar operator. It doesn't have any indices. So the way that works, if you just look at the two bases and write down the formula, you'd have an integral over these w's. There's some prefactors, which just come about from being careful. And then the thing that has an imaginary part are these Wilson coefficients. And then you have matrix elements of operators, which don't have any, which have a flavor index but don't have a subscript j. So this has a flavor index. Keep track of things. And then there's another one for T2. Some kinematic prefactors that are easy to work out, that just come about from the fact that we wrote the tensors in the effective theory and the full theory slightly differently. Okay, but these two guys have the same matrix elements of the same operator, and all this sort of tensor stuff is just saying that there's two different Wilson coefficients that you have to compute. And that's because you have these vector currents from the photons. OK, so this is what we're after. These show up in the cross-section. And what we're doing is we're writing at lowest order the things that show up in the cross-section in terms of effective theory objects, the Wilson coefficients and then matrix elements of our operators here, which is this thing in square brackets. And we're almost at what you would call a factorization theorem. Factorization theorem is a result for the cross-section in terms of effective theory, in our language, in terms of effective theory quantities, and that's going to factor the hard stuff, which is the pink stuff, which is in these Wilson coefficients, from the low energy stuff, which is in these operators.
So those matrix elements are exactly this bottom equation.
Yeah.
And what is square bracket d omega? You integrate over one of the omegas?
It's both. Yeah. You can write it like this if you like. Yeah. Any other questions? OK, so literally what I do is I take this formula and I plug it into that formula. And when I do that, I can do one of the integrals trivially because it's a delta function. All right, this one just trivial. And then I do this one with the other delta function. So both integrals are actually trivial. And I can write the result in terms of something that I'll call the hard function. Which is just the imaginary part of the Wilson coefficient. So, and I'm going to denote it in the following way. So this is W. The Wilson coefficient can depend on various different things. It can depend on W plus. It can depend on W minus. It can depend on the hard scale, which is q squared, or it could depend on mu squared. So W minus, when you do the delta function, gets set to 0. W plus gets set to something. And it's convenient because of the way this delta function is, with the kind of has a ratio. Because this function is a function of c, which is the ratio of two things, it's convenient to define a dimensionless z and only talk about a function of that dimensionless thing. And if you do that, then the final result for these kind of t's, which are imaginary parts of t's, and just put the formula together, I'll write one of them. And that. And then there's a similar formula for MT2 that involves H2 and H1. OK, so this is the factorization theorem And it came about, in some sense, just trivially. Once we knew how to write down the operators in the effective theory, we were basically done. And then the rest was just sort of algebraic manipulations, being careful about what momenta go where, and knowing what the sum of this formula for the matrix element is. This is the kind of important point. But in some sense, the effective theory from the get-go was already designed to factorize because we were integrating out the hard degrees of freedom right at the start. And so knowing what operators was really, and knowing their matrix element is really all we needed to do to get to the DIS factorization theorem. So if you ever look up the original way that this was derived, it was not that easy. This is actually something that's very complicated in a sort of traditional approach, but in the effective theory approach, becomes almost trivial. And this is an all orders result because we never expanded in alpha S. We just used symmetries, and we used the fact that we knew what form the operators would take when we integrated out the hard degrees of freedom. So any alpha S corrections that one might want to add will fit into this formula and just give a perturbative result for this H, which you would compute in perturbation theory, which people do up to 3-loop order these days. Now, if you ask about things like, I didn't write all the possible, I suppressed some things, right, like q squared and mu squared. If you ask about the q squared and the mu squared, then your Wilson coefficients do depend on q squared and mu squared. And the Wilson coefficients H here are actually dimension. The Wilson coefficients, the original ones, C, were dimensionless. So the H is dimensionless. I just pulled out the dimensionable factor so that that would be true. And so this guy can depend on q squared over mu squared. The fact that q squared only shows up there, that's Bjorken scaling. And if you look at sort of the perturbative result for a T2, then it vanishes at lowest order. So that's the Callan-Gross relation. So there's various things that are sort of encoded in this that come out kind of from the effective theory point of view in a very simple way. Okay, so let me write. So there's logarithmic corrections that involve q in the Wilson coefficients. It'll show up like that. So there's a mu also that you could add to this formula. So the way that I described it, we didn't think too hard about bare versus renormalized, right? You just take these operators. So far, they could have been bare. But remember that when you have C bare, O bare, in electroweak Hamiltonian, for example, that's C mu, O mu. So switching from bare and renormalized bare operators and coefficients to renormalized operators and coefficients is simply a matter of sticking in a mu here, and then you imagine that the renormalization has taken place. Okay, so we could equally well insert in these formulas a mu for that. And then what I'm saying about there being logs of mu over q will make a little more sense. So there's also a q. Squeeze everything in here if I want. Okay, now we're being completely honest about what it depends on. All right. So traditionally, what happens in the traditional literature, there's kind of people talk about factorization scales and renormalization group scales. So factorization scales, there's the fact that this parton distribution function is mu dependent. It's an operator that you have to renormalize, and we're going to do that in a minute. And so there has to be a cancellation, since this thing here is a physical observable and is independent of mu. There has to be a cancellation of the mu dependence here and the mu dependence here. All right? And that's this mu. So the thing that's multiplying this result here would involve a cancellation of mu dependence here and mu dependence here. So the same anomalous dimension would show up in both the H and the F. And then sometimes people also talk about mu dependence that's just sort of canceling within H itself. And they call that renormalization group. The renormalization group mu. Sometimes people vary these independently. In the effective theory, it's really simple. You really just have the classic setup of you have some hard degrees of freedom. In this case, we just can even think of it one-dimensional. You have some hard degrees of freedom that you want to integrate out. You have some scale, which we could call mu naught, that's of order q, where we do that integrating out. And then you can run down, or you could run in a more complicated way. So you could run the PDFs, which are sitting here at the collinear scale, which is lambda QCD. You could think of evolving them up to some scale and evolving the Wilson coefficients down and meeting somewhere. Okay. And so, yeah, it's just really a sort of classic running and matching picture. Here, I've just used the fact that I could run either one of them, or I could run both of them to a common scale. So usually we would pick mu to be either something small or something large, rather than running both things. But in general, you could think about running both things. And we talked about having anomalous dimensions for either one of these. And usually we just run one of them. OK, but it's no more complicated than the standard picture of integrating out modes and doing renormalization group evolution. So if we want to do tree-level matching, or one-loop matching, or any kind of matching, let me just show you tree-level matching. So tree-level matching, you would compute this forward scattering graph. And that will give you the other diagram that we drew. In effect, and so you want to match this guy onto that guy. And what you find is you find one tensor structure at lowest order. So C1 is not equal to 0, C2 is equal to 0, and that's the Kellen-Gross relation, which tells you about the spin of the object that you're scattering off. And this is how we know that quarks are spin a half, or one way we know. And then you can calculate C. And so the way that I set things up, C was complex, and then I had to take the imaginary part. So C is just this propagator, basically. And it's only a non-trivial function of W plus. There's some charges that sit out front. And so the only way that this guy depends on whether it's an up quark or a down quark is you have 2/3 squared or 1/3 squared. And then there's something that comes about from the propagator. It looks like this. And then I take the imaginary part. And then I get H1, which is a function of z, which is the C over x. So if I write it as C over x, like it shows up in the factorization theorem, then I'm getting a delta function of C over x, which is just coming from this. OK, so the lowest order H1 is just a delta function. And that's where the parton model picture comes from, because the parton model picture is that you think of C and X as being the same thing. And that's the tree-level way of thinking. And that's just satisfying this delta function in the hard function. And then you would get that the T is just given by the parton distribution at X, which is the external measurable thing. OK, so this is how all these classic things come about in the effective theory language. Any questions about that?